So let's do a volume. So this is the region R. It's bounded by two graphs, two parabolas, as you can read. And we're trying to figure out the volume of this solid when revolving it around the horizontal line y equals 3. So it's nice of them to remind us that y equals 3 is a horizontal line, but make sure you realize that. So it's going to be a pretty simple question, I hope. We're going to use the washer method. So we're going to draw our rectangle perpendicular to this axis of revolution right there. Um, so now we can start rattling off all the information that we have. So since the rectangle is vertical, this is definitely with respect to x. Our limits are where the rectangles can be drawn, starting here all the way to here. So we're going from x equals -1 to x equals +1. What else do we need? We need big R of x and little r of x. Big R of x is the measurement, the outside radius. Usually we say the measurement of the top of the rectangle to the axis of revolution. This is actually the bottom. Little r of x is the measurement for the inside radius, or in this case, this measurement from the top of this rectangle, and it's always to the axis of revolution. So now we're just ready to measure. So we have big R of x. If you're measuring a vertical line like this, you always do the y2 minus y1. Just look at your arrow points. Y2 is resting on this line y equals 3. So this would be y2 is 3 minus y1. The arrow point here is resting on, you can see this graph. This is the graph y equals x squared minus 1 because it's the parabola that's pointing up. So minus x squared minus 1. And that's that whole quantity. So now I'm ready for little r of x. And it's the same exact thing. Just look at your nicely drawn diagram and measure the vertical distance, which would be y2, the top of the arrow, minus y1. Y2 for little r of x that's on 3, just like big R of x. And then minus the lower arrow point, the bottom one, y1, is on this parabola that opens down, which is 1 minus x squared. So that's it. We're done. It's going to be a simple integral because they're all polynomials. So I'm going to set it up and do it in the calculator. So the formula for using a washer method is the volume is pi, your limits, which I already have, r of x squared minus little r of x squared, and that's it, dx. So I'm just going to use everything I put up here. So we have pi times the integral with respect to x from -1 to 1 of r of x squared minus, that was big R of x squared, now little r of x squared, dx. And that's your answer. So you can easily do this with a without a calculator. It's just kind of a nuisance. You'll have a fourth degree polynomial. I'm going to grab my calculator. I calculate it. So here we go. I'm on a, you can see I'm on the wrong mode here. I'm in polar mode, so we're going to switch back to the regular function mode. Clear all this stuff. So I'm going to type it. Well, we have 3 minus x squared minus 1 squared. So I have a, let's just type it in exactly how it is. Three minus x squared minus 1 quantity squared, and then minus 3 minus the quantity 1 minus x squared, and I know you could do some simplification with the 3 and the minus, but we'll just put it in exactly how it's written. And I just have to remember here that I did not put in the pi, so I'm going to have to keep that in my answer. Let's hit the graph. Oops. I remember I knew that when it was graphing, I left this straight parenthesis in here. So I have to integrate from -1 to 1 and look at my graph. My graph is going exactly like the positive part from -1 to 1. So I think I'm in good shape. That's usually an indicator. So let's calculate the integral from -1 to 1. And I'm getting exactly 16. That's interesting. So, and that makes me feel a little confident. I don't know why, but it does. So the answer to this question is, don't forget the pi. 16 pi. That's it. Pretty easy. Just draw a nice diagram, measure, and it actually is very easy. So thanks for watching.